Okay, back to where we were before. Okay. These are the rest of our in-class problems for today, and after we finish those, that'll be about it. We will have some problems for you to practice that we will send out in a couple of days. What's the smallest positive integer with exactly 10 factors? What about 18 factors? And find all the two-digit numbers with exactly 12 factors, and how many three-digit numbers have exactly 3 factors? Oh yeah, please specify which one you're submitting for when you go to submit these, and I'll rename the TAs so you can message them again. All right, so I see somebody got number 1. Let's quickly go over this. 10 factors. How does 10 itself factorize? Oops. Sorry. We're having some technical difficulties tonight. Anyways, 10 can factorize 3 times 5 or 1 times 10. Steven, do you want to say something about this problem?
Yeah, so after you factor into 2 times 5, 1 times 10, you just basically kind of see that 1 to 10, 1 and 10 doesn't sort of just really works really bad because it's p to the ninth and it gets too big, yeah. So I just eliminated the possibility. I mean, I didn't even try to do it.
Okay, and then from there, 2 times 5 would correspond a prime number to the 4th times another prime. We want to take the smallest primes possible, and we want to have the smallest prime occupy the bigger power. So it'd be 2 to the 4 times 3 would equal to 48 is our optimal solution. All right. As he said, like oftentimes this kind of extreme factorization is suboptimal for most problems, like the smallest number, this and that. So we don't even need to consider once we notice that. For 18 factors, similarly, 18 can factor as 1 times 18, but the 17th power is like way too big. You don't consider that. Factors 2 times 9, which will also be too big. And 3 times 6, and it can also factors 2 times 3 times 3. Make sure you exhaust all of these factorizations. Okay, so we don't need to consider the 9th power since that's going to give us a couple thousand. This 3 times 6, p squared, q to the 5th. We want this to be 2 and this to be 3 if we are to get our number, which give us 32 times 9, 288. Oh. So, and while this would give us something even smaller, be pq squared r squared. Again, smallest prime to the biggest power when you're minimizing is 180. So 48 and 180 are our answers for this problem. Okay. Okay, now that we've gone through that, we can go ahead and do the rest. I'll say the second problem right here is like the kind of trippy one. And because I asked you to explicitly list them too, it's easy to miss one or two. So yeah, just take extra caution with that one. And make sure you exhaust all the cases and like actually try before you just dismiss it as being invalid. And so your answer to number 2 should be a list of numbers, like a list of 2-digit numbers that have exactly 12 factors. Notice that it's not the number of numbers. All right, I'm seeing some of you guys are getting the answers to number 6, but I don't see anybody who's gotten all of them yet. All right. Um, okay, so easy, please, next time private message me your answer, but you actually got it. So I will just go over it now. First, we want to factorize 12. Yeah, you can send it privately to me, and sorry I should have enabled direct chat too. So 2-digit numbers with 12 factors. 12 can factor as 1 times 12. Okay, that's not going to be a 2-digit number. It can also be 2 times 6, which is like p q to the 5th. 3 times 4, which is p squared q cubed. 2 times 2 times 3, which is p squared qr. Where p, q, and r are all primes. This is just like generic notation. For this, obviously this has to be small. We notice the only prime that'll work to the 5th power is 2, and 2 to the 5th times 3, the next smallest prime, just barely makes it at 96. And that's obviously going to be our only one for this case. For this case, p squared times q cubed. We should try 2 cubed because, like, you know, small prime to the big exponent first. 2 cubed. Okay, well, what 2 cubed times what? We'll keep it as a 2-digit number. Anything up to 12. 12 perfect square is less than that, so we can only have, looks like, 3 squared. This is equal to 72. We can also try 3 cubed, but like 3 cubed times 2 squared is already 108. That doesn't work. So now we come to our last case, p squared qr. This has like the most out of all of them. Just to case work on which one is squared first. 2 squared, we can multiply by any number any like product of 2 primes less than or equal to 25, or less than actually. Note that we don't want to include like things that are a product of 2 primes where one of the primes is 2. So here we can have, let's see, 15 and 21. This, and also actually, oh wait, no, that's a different case. So 15 and 21, this gives us 60 and 84. And I was about to jump right to case where it's 3 squared. In this case, we can multiply by a product of 2 primes that aren't 3 less than or equal to 11. 2 times 5, this gives us 90. We notice if we start going higher, there's no more cases. So our answers in order are 60, 72, and sorry, I erased it by accident. 60, 72, 84, 90, and 96. All right, so how many 3-digit integers have exactly 3 factors? So I see people have gotten this too. It's just 7 and 3 factors. Well, we know it's got to be a perfect square, right? Because it's odd number of total factors. But not only that, we know that it has to be like a prime square because 3 can only be factors is like, 3 because it's prime. So it must be this form. Well, how many primes have a square that's 3-digit? Not that many, actually. The last square under 1,000, which is the last 3-digit square, is 31 squared. This actually is one of the prime squares we have to count. And the smallest one would be 11 squared, also a prime. All right, Steven, do you want to explain? Do you have a question?
Um, I mean, yeah. Okay. I might just explain. Like, I mean, I just listed it out.
Yeah.
So basically, I just listed out of all the primes, and then because I know that 11 is 121, I just did it all the way into 31 because sort of 37 is really far away from 31, and it since 31 is already 961, you can probably tell that 37 would be way over.
So yeah,
So
that's right.
yeah, so yeah,
These are
I mean
these are
just
all the primes, like he said. You just list them out. You really need to check. All you need to do is first you find the upper and lower bounds, which are actually prime themselves, 11 and 31, and then you list out all the possible primes that have squares in between these. There's your answer. There's 7 of them. If you're curious, they're 121, 169, 289, 361. Sorry for the handwriting. 529, 841, and finally 961. Those 7. So those are your squares. So that's pretty much it for today. I guess like at its core, like this factor counting stuff really is not too difficult. You just have to be careful and really know what you're doing. And class is actually done on time. We will assign some like a bunch of like similar problems to what we did in class for homework as usual. Next week, you will start doing practice AMCs for homework, so be aware of that. Oh yeah, and a good amount of you, like well over half of you, are completing the homework on time. So keep it up. And for those who aren't, you should like please start doing the homework, because it will help you prepare for the AMC a lot. And with that, class is officially over, and you are free to go. Happy New Year, everybody, and have a nice holiday.